A basic exponential function has the form f of x is equal to a to the x. It's called exponential because the variable appears within the exponent. The value a also has a term, and it's called the base. So I'd like to look at a graph of f of x is equal to 2 to the x. Here the base is equal to 2. I think the best way to approach this is to make a table of values. So I'll just choose some values like -3, -2, -1, 0, 1, 2, and 3. We'll plug these into the function and see what we get back. So maybe I'll start with looking at 0. The function at 0 is 2 to the 0, and that's equal to 1. So at 0, we get 1 back. If we look at 2 to the first, okay, that's just 2. So at 1, we get 2. 2 squared is 4. And 2 cubed is equal to 8. So I've plotted those points on this graph. Now, if we start putting negative values into the function, like let's start with -1. 2 to the -1 means we're dividing by 2 instead of multiplying by it. So you can use a decimal of 0.5 or the value 1/2. I'll choose to write it as 1/2 over here. But at -1, we divide by 2 instead of multiplying by 2. If you look at 2 to the -2, this means 1 over 2 squared. So basically the negative exponent puts the base in the denominator. And here the value is going to be 1/4. Or if you'd like to use a decimal, that's 0.25. I'll go with 1/4. So it's going to get difficult to graph this, but at -2, it's equal to 1/4. So I'll just put some value that's pretty close to 0. And if I check 2 to the -3, this really means 1 over 2 cubed, and that's equal to 1/8, or 0.125. At this point, I think it'll kind of vanish a little bit. It's going to be so close to 0, but I get the idea. As we move in this direction towards -infinity, these values get closer and closer and closer to 0. And as we move towards positive infinity, the values start to increase like this. If I draw the graph going through these points, this is a basic exponential function for 2 to the x. I think one thing to point out here is that the base a in my example was greater than 1. Whenever this happens, like you could have the function 3 to the x or 4 to the x, your graph will still resemble this shape, and it's going to be increasing as you go in this direction. So now that I have the graph, I think we can figure out the domain and range. The domain of this function is all real numbers. You can put any number that you want in place of x, and you'll always get something back for y. But the range is not all real numbers. When you put a value in place of x, it's always going to be positive. If we go in this direction, it's getting really, really close to 0, but it never actually equals 0. So the range is going to be 0 to infinity. Maybe one other feature of this graph is, just like with rational functions, y equals 0 is a horizontal asymptote. The reason is that this graph keeps getting closer and closer to y equals 0 as you head towards -infinity. So I'm just going to note that there is a horizontal asymptote on this equation, and it is y is equal to 0. And I think that is it for looking at the graph of 2 to the x. Let's compare the function f of x is equal to 1/2 to the x to our previous example. So we're still dealing with an exponential function, a basic one, something of the form a to the x. But now the base in our example is less than 1. And maybe more specifically, is greater than 0. Will having a base that isn't bigger than 1 affect the shape of the graph? It's going to look a little bit different. So we can approach this one the same way by getting a table of values and seeing what we end up with. And I think I'll still use -3 to +3. So all I'll do is plug these values into this new function, look at the graph, and see how it compares to the previous example. So I think it's simple enough to start with 0. So let's see. I'm now looking at 1/2 to the 0 power. Well, anything to the 0 power that's non-zero is equal to 1. So there's no difference there. At 0, you still get 1. But this time, if you put, let's say, 1 in place of x, well, 1/2 to the first power is just a half. So we get this spot here. If we put 2 in place of x, well, you would square the numerator, you would square the denominator. 1 squared is 1, 2 squared is 4, and you get a fourth. Again, you can use decimals for these if you'd like to, but I'll put 1/4 in place here, and just note that, okay, we're getting closer to 0. And if I continue this, I get an eighth. So something even closer to 0 here. So this is different. This time, as I head towards positive infinity, the values aren't going up. Instead, they look like they're getting closer to 0. So I wonder what's going to happen if we look at the x values going in this direction. So let's check out -1. If we put -1 in place of x, 1 is raised to the -1 power, but so is 2. What this is going to do is flip this fraction. It's going to give us 2/1, or just simply 2. That's what the negative exponent would do in this case. Last time there was just a 2 and it placed it into the denominator. Here, 2 is in the denominator and it moves it up to the numerator. Since the number here was just 1, we don't have to write it at the very end. And this is our value. At -1, the value is 2. This pattern will continue. So if you look at, let's say, 1/2 to the -2, the negative means you're flipping this fraction, so it's going to give you 2. But now, since I have a 2 here, I'm squaring it as well. So we get 2 squared, which is 4. So again, the idea is the negative flips the fraction, and then we have to still square what's left over. So 2 squared is 4. And lastly, if we look at 1/2 to the -3, that negative flips the fraction. I don't need to write the 1 in the denominator. And I'm left with cubing 2, and that's equal to 8. So we have 4, and we have 8. If I draw the function that goes between these points, I get something that looks like this. And if we compare this to the previous example, it's just a reflection over this axis. So the graph is the same. I'd say the difference here is the graph is now decreasing instead of increasing. So the big takeaway is, if your base is between 0 and 1, like a half, that means your graph is going to decrease. If the base is bigger than 1, like in the previous example it was 2, that means your function is going to increase. The domain and range are still the same. The domain is still all real numbers. You can put any number you want in place of x. And for y, all the values you're getting back are positive. And it's also worth pointing out that y equals 0 is still a horizontal asymptote. And that is it for this example. So what does a graph of a more complicated exponential function look like? Like here we have 2 to the x plus 5 plus 3. So we can address this by using transformations. If I look at this equation, there's 2 things that are different. I have an x plus 5 instead of x, and I have a plus 3 outside of the function. So the original function that we're looking at is still 2 to the x, and I know the graph is going to go left 5 places and up 3. So I'm going to jot that down. This goes left 5, and it goes up 3. So if you understand the function 2 to the x, that's what's graphed here in red, it's easy just to take a few points on the graph and move them through this process. So let's see. The first thing I'm actually going to do is say, well, 2 to the x, which is graphed here, still has this horizontal asymptote of y is equal to 0. If we move it left 5, that doesn't change the horizontal asymptote. But if we then go up 3, that moves the line y is equal to 0 to y is equal to 3. So I'm going to put this in as a reference to say, okay, at y equals 3, there is a horizontal asymptote. To complete this graph, I'm just going to pick a few points and see where they go through this process. So this is the point 0, 1. If it goes left 5 and up 3, we end up at negative 5, 4. So I'm going to plot that point. If I do this with the point 1, 2, we will go left 5 and up 3 to negative 4, 5. So here's the point 2, 4. I'm going left 5 and up 1, 2, 3. So that's negative 3, 7. And the last point here, I'm going left 5 and up 1, 2, 3. I get the point negative 2, 11. So the graph has the same shape of the function that we start with, except it's going through these new points. So if I draw that, I get this as my equation. So understanding a basic exponential function will tell you what more complicated ones look like if you're using transformations. So I got the last thing here is talking about the domain and the range. But if you understand the graph, these things are easy to see. Okay, now the y values are starting at 3, and they're going up to positive infinity. So I'm going to start with that first. 3 to infinity is the range. And the domain is still all real numbers. You can put anything that you want in place of x for this function and get something back. And that is it for this example.